All right, Mr. Phelps, we're just going to power on here. Hopefully the other guys will watch the video. It won't be too long today.
Okay, sounds good.
And then if you have questions on anything from before, just stop me and I could stop the recording and go over questions or whatever.
Sweet.
Whatever. All right, so just to review 5-1. We did yesterday, I went over 5-1, 5-4, and 5-3 just really lightly. And 5-3 is really easy with force equaling mass times acceleration, and we can find the work, the physics work done in the situation by doing the integral. So instead of, I probably won't go back over that today, but I do want to just do maybe one example of the area problems so that we got something to base what we're doing on today. So what we did yesterday first was area problems between two curves on a graph. So let's look at, here's a nice one. So if you have two curves, here's one of them, y equals x squared and y equals 4x minus x squared. We can find the area by taking the the top curve minus the bottom function. We just have to graph it and see which is which, dx, and take the integral from, find the two places. Sometimes they'll tell you the limits of integration, what numbers to go from where to where, and sometimes we have to figure it out ourselves. So I just wanted to do this one because that's the little bit harder way. So our first thing is to sketch it and see which is the top one, or put it in a Desmos or graphing calculator. And I know right off without even anything that the first one I wrote, y equals x squared, would be pretty much like that. And then this one's going to be a parabola cupped down. So, and like if we're doing it fully by hand, we could just make a table for that, but I don't want to waste time. It's not a waste of time, but I want to take up more time on that. So this is going to go from here up like this, there. So I'll make it green. That's the second one. And what we're looking for is the area between them right here. What's the area? The exact area of that we could find. So now I know from the sketch that this is the one on top. This is going to be the one on bottom. And even in Desmos, I could avoid the algebra too and see that the left-hand boundary of the region is 0. And the right-hand one is right at 4. But we could also find that with algebra. We could set them equal to each other, like this. This equal to this. And then just do some basic algebra. Get it all on one side. Factor out 2x. So x, the solutions would be x equals 0 and x equals 2. Hey, what did I do? I made a mistake, huh? Hold on, maybe my graph is wrong. No. 4x minus x squared goes right there. And then x squared. Oh, there we go. Yeah, it was over a little too far. So this is 2. So good thing I checked it. I checked it with algebra because I was rushing through the graph part. So this should be 2, my bad. The picture still looks kind of like that, but so I'll leave it like that. Then we take the top integral substituted in here. And then the bottom one was x squared. go from 0 to 2. And then combine like terms. And then integrate it up. So add 1 to the power, divide by that. Add 1 to the other power, divide by that. And it's going to go from 0 to 2, which is nice when that happens, because the 0, when we substitute in the 0, it's just going to zero out the whole expression. So it won't be too complicated. And I didn't assign too many complicated ones, but they're just a little bit time consuming. And since there's the algebra, the visual, and the calculus involved, it just is a little bit of a brain workout for a lot of people. For me, it is anyway. So let's see if I've got room here to finish that. This is going to simplify down to, well, I'm not going to erase it, Jenny. There. That's going to be 2 over 1. So 2 times, substitute this in for x. And then the second x. And then officially we would substitute in 0 next. But that's just going to zero out. We can focus over here. 2 times 4. 2 to the third is 8 times 2. So that's 16 thirds. And then we need a common denominator. So just to review that, this is 8 over 1, but I want it to be over 3. So that would really be 24 thirds minus 16 thirds. So the answer is 8 thirds. And it's really an area, so it's square units, but we never write the label on these, which bugs me. But we don't when we're doing these just graph ones, unless it's a story problem, like we have one where we find the volume of a liver. Then we do it in units, so centimeters, cubic centimeters. But so that would be the answer there. I know that's a lot to take in first thing in the morning, but does that make sense? And do you have any questions about that?
Yeah, no, I think I kind of get it, just putting some of the stuff we learned together for this.
Great.
I've always been bad at finding areas of a graph though, so this is gonna take me some practice.
Well, I'm gonna show one more where it goes sideways the other way, just so you could see the 2 types of things that we did. So number 20 in the book, in this section 5.1, is x equals something, and then, oh no, that one's not that good. That one's all mixed up. Let me do one that's not so bizarre. Here's one. Okay, this is 17. It's better. X equals 2y squared, and x equals 4 plus y squared. So again, the steps are to sketch them. That's harder for most people to sketch by hand just because they haven't had as much practice. I think of them as graph on their side, lazy graph. So we sketch them or use software, which might be easier. Either way is fine. So we sketch it first, then we have to find the limits of integration if they don't tell us. Sometimes they'll say, do it from y equals 2 to y equals 5. and sketch it, and then they give you the numbers. But this one, we have to find them. So if I go to sketch this, this is a rough, kind of rough sketch, but like that last one. X equals 2y squared. It's a little bit tighter than a regular parabola, going that way. Here's our x-axis and the y-axis. And then 4 plus straight up y squared would be about here. Not perfect and less tight, so it'd be a little wider. And so we're going to be looking at this. We want the area of this region. So it's super great. It's a super fun tool to be able to find the area of curved things other than just like circles and ellipses and stuff. So now we can find the area of any kind of curve, really. And then this, when it's sideways like this is called the right, just by looking at the picture. That's the right-hand curve, the red one. And this we call the left-hand curve. So for this area, it's going to be the right curve minus the left curve, the function for them. And then it'll be, instead of dx, we'll use dy. And we'll have to find what are our y values that we're going from where to where. So we'll figure that out next. I'll put it with algebra because I know my sketch isn't perfect. So
On
in
the
these
integrals,
sideways.
are those zeros?
What?
Like
Oh no,
eight.
no, they're just blank, empty
Oh,
box.
okay. Oh, I see
Yeah.
what you're saying. The
Good
squares,
question.
huh?
Yeah.
Okay. I was like, wait a second. Sweet.
So let's make a quick algebra setup for the limits. So set 2y squared, set the functions equal to each other. And this is, all this stuff just brings back basic algebra, intermediate algebra, basic fraction and integer, negative and positive stuff. And it's a lot to pull back into the front of your brain. So I do understand. That happens to everyone. Me too. I haven't taught this in a couple years, so I was a little rusty. Y squared equals 4. So y is going to be plus or minus the square root of 4. So plus or minus 2. So that's nice. Here's -2 and +2 on the y-axis. I put them here. And now I can notice, I'll plug in the functions next for R and L, but I could notice that also this is perfectly symmetrical. This one is. And so I really could, I'm not gonna because I'm showing this example just to do the whole deal, but I really could just find this area and then double it. So if you do notice that it's symmetrical, that could save you time. But this one's not too complicated, so we'll be fine doing the whole thing. So let me get it plugged in here. So the function that was on the right, the red one, is 4 plus y squared minus the function that was on the left, 2y squared. And then the d whatever always matches the variable that's in your brackets. So if it was x's, it would be dx. If it was y's, it would be dy. Because we're still thinking of like infinitely narrow rectangles defined by the y-axis right now. So I'm gonna erase my graph, and it's good to kind of estimate too, like, oh, I don't know. I would guess maybe it's going to be around, I would just guess. So it's good to just look at it, make an educated guess. What do you think the area is going to turn out to be? So you have that side of your brain turned on that knows how to calculate length times width. So like, this isn't going to be the answer, of course, because it's more refined than that, but let's come back now. If I just looked at maybe a triangle area right here, that would approximate it pretty well. So if I used my old-fashioned triangle area formula, 1/2 base times height, then I could get kind of a rough idea what the area is going to be. And that's not required, but it just helps turn that on in your head. So I would guess around 8, but that's just really rough guess. Okay, then before we integrate, we're going to combine like terms. 4 plus y squared minus 2y squared. So it's just going to combine to this. And then take the antiderivative. From -2 to 2.
The things on the top of the integral, is that just like the domain or whatever, or what would you call it?
The numbers in there?
Yeah, on the top and bottom, those are
They're called the limits of integration.
okay.
That's the interval that you're looking at.
Interval. That's the word I was looking for. Okay, just making sure. That's what I thought.
Good question. So I'll substitute in the top value of that into the limits of integration, or the interval, 8/3. So that's putting in 2. And that number is always bigger than that number. Otherwise, you'll get your sign backwards. And then subtract and put a bracket around so that the signs stay right. 4 times -2. And then -2 to the third is -8. So I'm just being really careful with my signs right here. Because our area, I also mentioned this yesterday, that now in this section, area is going to be always positive. We'll never get a negative area. And if we do, that means we have to take the absolute value of the negative part. So we just want area to be all positive pieces, even if they're under the x-axis or over it or whatever. So let's see if this comes out right. 8 minus 8/3 minus. This turns into a big plus, so that'll be minus. Get back the black with the. Yep, 16 minus 16. Then I combine my whole numbers, combine my fractions with common denominators, and then get a common denominator happening for this. So 16. I want to put it over 3 instead, so I have to multiply it by 3. That's an 8. 48 minus 16 all over 3. -48 minus 16. And it's 32/3. We just leave it like that, improper fraction. So that was the answer to number 17. And that's the area between the curves. So again, those are harder, the sideways. The functions that have y in them instead of x, that look kind of sideways, but I think I didn't even try putting one in decimals, but it should work. Let's see what it does while you think about that. See if you have any questions. X equals 2. Yep, yeah, decimals graphs them just fine sideways. The TI calculators don't, unless you have a really newer one, because TI calculators only deal in functions. 4 plus y squared 2y squared. Yeah, it's pretty sweet. Looks like a sideways smile. All right, let's see. Do you have any questions about that? Your assignment will give you plenty of practice of that, so that'll be good. Okay, so then I'm jumping over to section 5.5 because this is pretty easy. So we just did this right at the end yesterday. Average value of a function. So I just want to do one example of this.
When you're plugging in on the other ones, do you use those intervals?
Yep.
Okay.
Yeah. You always plug in this one first, and then minus sign and bracket, and then plug in the bottom one. Yeah. We could practice, maybe we'll practice one more like that too in a second. Yeah.
Okay.
Just to get the good feel for it. So the average value of a function, if it's a continuous function, we write it like this: F average. I think it looks like a fave. And these are B and A are the edges of the interval. So it has to give you what interval it wants, which I will give you. And then they go here too as your limits of integration, and the function goes inside like that. So that's like, like say we're looking at our heart rate during a workout, and it's like, then like my workout watch will tell me what my average heart rate was. So it's that idea. So it's not always peaking up here. It's not always down low, but the average of all that, if we could add those all up, but there's an infinite number of values because it's continuous. We could always find more values between other values. So we couldn't just sit down and crank it out number by number. We wouldn't get a very accurate answer. But this would get our answer really beautifully. So we could use integration for that. So anyway, let's say, I'll erase my heart rate though, because it's not going to be that complicated of a function. That'd probably be some kind of a trig function. Let's say we're looking at this function. F of x equals 1 plus x squared on the interval -1 to 2. So this is our example. I always think it's a good idea to just look at it. So it's our regular parabola shifted upward. And it's only starting at -1 though. So it's just going to be like, stop there. And it doesn't go on and on. This would be an endpoint. So we're looking at that. If we could add up all the y values and divide by how many we added, like we do a normal average, we could try to do it by hand, but this is way smoother. So let's do it with our integral. So stop and slow my roll a second and label things. This is A and B. And this is the function. So I'm going to write fave F average equals 1 over, and when I do these, I always forget this part. I just rush in and do the integral and get the wrong answer. But we want the average value, not the whole area under the curve. So this is that b, the b minus a part, and then integrate from -1 to 2. You still use those a and b again, and then the function 1 plus x squared dx. So that was just plugging in from the function, and now I'll erase this so I can keep working on the same page. And again, it's always really good. Never get too overwhelmed that you might be like, what the heck is going on? Like, when x is -1, this would be actually, it's a little bit drawn poorly. So it'd be up at 2, y equals 2. When x is 0, y is 1. When x is 1, y is back up to 2. When x is 2, it goes up to 5. So that's what, these are the y values of our function. And somewhere in here, of course, there's like 3, 4. If I could add all those together and take the average, like if I just took those 4 numbers, 4, 5, that's 10. Divide it by 4 of them, I'd get 2.5. That's a really rough though. Like, I don't think that's going to be quite accurate, but it's always good to just be like, well, maybe it's around, that's the average value, maybe, you know, just to get an estimate. But that's really rough, because we want infinite number of y values. So we can do it this way, we get our exactness. Whoops, times. Let's see, take the antiderivative of this. So you're going to have x plus, add 1 to each power, and divide by that power. And then we're going to go from -1 to 2. So this is a definite integral. This is a 3. And then I'm gonna do the substitution in there really neatly. One-third, big bracket. First, I'll plug in the 2 to both of them. Then minus, because I'm taking the high minus the low. Always I put a bracket right here because of the sign issue. And then plug in -1 to both of them. And simplify it, and keeping it in fraction form is one of the hardest parts of it, I know. And there's one thing I forgot to say about all this in this section yesterday, so I'll just show the mean value theorem briefly for this one. So let's keep going. 1/3. I'm gonna take off the parentheses and deal with the signs first. Simplify these. Minus -1 and minus -1/3. They're both going to go positive. And I told Miles this yesterday, and it happened to him too. But this is the biggest problems people have with integration, honestly, are just messing up their signs. It happens to me too. Or like I said, I'll sometimes forget to stick this in the front. It comes out way wrong. So I try to rush. So that's my problem. 2 plus 1, I could combine pretty easy, right? And 8 plus 1 is 9. 9/3 is 3. So this is going to be 1/3 of 6, actually. 1/3 just hangs out in the back, out in the front until we're done. There, equals 2. So the average value of that original function of y equals 1 plus x squared, the average is 2. The average y value. Okay, on that interval. So remember the interval went from when x equals -1, then y equaled 1 plus 1. And when x equaled, the top point was 2, excuse me, y equaled 5. So the average y value overall for that function on that interval is 2. I'm going to keep rolling with this function, 1 plus x squared. On interval -1 to 2, same like we were doing. The definition of the mean value theorem, to me, it seems kind of obvious, but we just put it on here. So if you have a continuous function on an interval, so it doesn't have to be continuous everywhere, but just in the neighborhood you're looking at, then there exists a number. Here, let me write it this way. A number C in the interval such that f of c equals f av. Let me write it the right way. And our formula for the average value of the function. Then they just write this in other words part, where they multiplied both sides by b minus a. So, but the most important part of this was, remember, we got that our average value was 2. So that's the y value. We could find out what, so if f, in this situation, the f average was 2, that's y. We want to figure out what is c. Find the x value that coordinates with that. We would take 2 equals the original function. Subtract 1 from both sides. X squared equals 1. And then take the square root of both sides. So x equals plus or minus 1. So look at that. We got c equals -1. That's in our interval. And c equals 1. It happens in both places. So all it's saying that if there's an average on a smooth curve, somewhere there has to be an x value that equals that average value, an x and y coordinate that equals it. So that's all that's saying. It's a lot of wording for that. And I'm not going to ask a question on the exam, like state the mean value theorem and prove it or anything like that. But it's just good to be aware of that I don't know. To me, it makes sense. And again, the curve was like from here to here. And when y equals 2, that was our average value. So x could be -1 or 1. If c equaled to -1, f of c would equal 2, which is the average value. Same as the other one. There's not usually 2, not always, sometimes if c equal to 1 to get the jackpot of getting c 2 values for c, then f of c was 2, which was the f average. So there's, on this interval, there's 2 places where it actually happens. So you would never skip over your average value. It wouldn't be possible. That's all it's kind of saying. Or why don't we, well, let's practice. Let me let you practice one here. Not let you. Go ahead and we get one from the review problems, because these are, you know, kind of tired old problems. On the interval from 0 to 4. This one is. So I'll put the formula here, and I'll just pause this so you can work on this yourself for a few minutes. Get the feel of it. So remember, first we'd sketch it and then calculate. I almost forgot the important estimate. Guess what it's going to be? Remember when I did that rough estimate, I got 2.5. I wasn't that far off, actually. Sketch, estimate, calculate. And then try to verify. If you have software to work integrals, I can't stop you from that either. I noticed, someone was using their device to calculate the integrals. So that's okay with me. And if you understand how it's generated, where it comes from, you'd be able to do it by hand if you had to, just in case you end up somewhere where they don't let you use it. I don't want anybody to be hobbled by their software. I think it's really useful though, so I'm not against it. Okay, now I'll pause this. Because I promised we're not gonna go that late. So it was from 0 to 4, which I erased somewhere. So that's A and B. So it's gonna be 1 over B minus A. A and B go here. The smaller one is always on the bottom. X to the 1/2 dx. Label what I'm doing. See if I can fit it here. F average. There we go. 1/4 x to the 3/2 divided by 3/2. 0 to 4.
Something wrong. I got 16/3.
Oh well, we'll watch this and see if you could catch it, or if you want to send me a screenshot or show me your work, you could do that too. So let's see. Divided by 3/2 means we're multiplying by 2/3, really. So we can put it out in front and then just ignore it for a minute. And x to the 3/2 is the square root of x to the 3rd. Because those are constants, so I could put those out front like that. And then reduce here while we're at it. So it's going to be 1/6 out here. And then the square root of 4 to the 3rd is 2 to the 3rd. So that's 8. So that one's going to be 8. And then the other one's 0. Equals 0 to the 3rd, which is just 0. So I'll put it there because it's officially there. I don't always do that step because it's 0. So then 1/6 of 8 is 8/6. Which we do. Do you see what happened, Trey? Are you okay with that?
Yeah, I wrote something down wrong. It's just a human error rather than a math error.
All right. Okay. Angel, are you okay with this?
Yeah.
Okay. Great. All right, so that's average value. The one thing, I'll just show the formula that we did for the work. If I could see where I put it. And so this was there, section 5.4. In physics work, this is really super basic physics, is mass times acceleration. Or you can also call it the force times the distance traveled. If there's a force pushing on something. W is in a Newton meter if you're in metric, which is called a joule. I think honestly the trickiest thing in this is that you have metric and US customary alternating. Otherwise the math is really easy. The force, if it's in US customary, is in pounds and the distance is in feet. So the work is in foot-pounds. And then if they give you a function, the work is the integral or the area under the curve of the function. So that's pretty much it right there in a nutshell. So some of the questions I assigned are super easy, just like how much work is done lifting a book off the floor to a deck 0.7 meters high, things like that, where you just multiply. Just if you're in metric, if it's the simple problems, if you're in metric, you also have to account for the force of gravity, which is 9.8 meters per second squared. But in US customary, we don't multiply it times -32 feet per second. So in US customary, it's all accounted for it somehow. And I was trying to explain that yesterday. I've never really understood why they don't have to account for gravity. Maybe pounds, because weight.
Pounds is already including gravity.
Yes, thank you, Trey. Extra credit for you. Yes. Pounds is already including gravity, so we don't have to worry about it. But in metric, we multiply it by that also.
Mass. Oh, it makes sense. Never.
So like what I was just saying, I'll just do 2 examples, 3. I'll do one in metric, one in US customary, and one with an integral. So if you have a book that's 1.2 kilograms and you're taking it up off the floor to put it on a desk, and the desk is 0.7 meters high. We want to know how much work is done. So work is the force times the distance, but the force is the mass times gravity. So this is just in metric. We just have to remember to not forget the gravity. And that's the 9.8. So this one would just be, where are we at? The mass was 1.2. The gravity is 9.8. And the desk is 0.7. And we're all set. We're in kilograms, we're in meters. So it's all good. So, and then we end up with an answer. Tell me what you get. And you put J for joules. Boy, if I hadn't already had all my kids, maybe my next pet, I'll name Jules. It'd be cool. Spelled that way though. People would be like,
This reminded me of physics. Don't miss that class.
it is physics. Yes.
Having to do the heat and energy and stuff like that. Remembering all those formulas. Oh,
This is,
And then,
yeah, go ahead.
like they would make you like do conversions, like the most bizarre conversions too, to like make sure you get the right answer. 'Cause there's some certain formulas that require certain like measurements. So like the answer needs to be meters, but you're given millimeters and like kilometers.
Yep.
Yeah,
Sweet, beautiful physics.
I
it's
love
giving
physics.
me flashbacks. I love physics, but man, it's just some of the problems that were like,
Yeah, it's a
God,
lot.
man. I took
I've
AP physics and it was just,
Ooh, good for you.
Nice.
yeah, it was,
Did
I
you-
passed with the B. But
That's great, Angel.
yeah,
I've never taught
I
physics.
love the lecturer.
Uh-huh. Who was
He
the
was,
lecturer? Go ahead. Sorry.
his name was Dr. Smith. He was a alumni from Stanford. Me and him got along pretty well.
Wow, cool.
And I'd always go in like after class to like understand the material better.
Nice.
Yeah. What were you about to say though, Jenny? Sorry, I kept interrupting you.
No, you're good. I was getting all excited about it. That's all. My dad taught physics. I've never taught physics, but I think it'd be really fun. But that's all.
I think you would
And
love teaching physics.
I think I would love just to take a bite out of those problems. But but this, what we do in here, it's way easier. I mean, it's just this, almost just this. This is just kind of showing you that you can use integrals now because they have like calculus-based physics and then physics without calculus. In the more advanced levels, it's calculus-based. So this is just kind of giving an example, but I didn't even do an example with calculus in it yet. So, let's go on. But did you have something else to say too, Trey? I think I'm interrupting everyone today.
No,
Sorry, guys.
no, yeah, I like physics too. I like it just works.
Nice.
Wait,
Here's a similar one, like I promised with US Customary. So the second question is how much work. So we want to find the W if we have a 20-pound weight. So just remember, shift your brain back and forth, weight, pounds, and metric. It's so stupid that we have to do that in our country, but I guess it doesn't make you dumber, right? It's good practice for your brain. 6 feet off the ground. There we go. So in US Customary, then the work is just going to be the force, which is the 20 pounds, and the distance, which is 6 feet. That's it. So you'll get 120 foot-pounds. And that is all to that one. But now I'll show you two that involve calculus, so you can have a little excitement in your morning. Not that this wasn't exciting so far. I know. Okay, example 3. Now we're talking about the particle that's x feet from the origin and the force of x squared plus 2x pounds acts on it. So let me just write the force. So already I know my answer is going to be in foot-pounds. So I'm going to have to find the work. And I always write myself a note because I'll get into the math and then forget the label. It's what I have a problem with that. So, and then they're going to move it from, so we're picturing we're on a number line pretty much. Move it from x equals 1 to x equals 3. Those are our limits of integration. So the work is going to be the integral of the force from 1 to 3 in this case. So I didn't write that. Oh, here's a spot for it. Work is always the integral of the force.
Oh, shoot, I just realized the time. I might have to sign in my internship after this problem, Jenny, if it's okay.
What'd you say?
I might have to sign into my internship after this problem.
Oh yeah, that's fine. I'm almost done. I'm not going to do volumes today. I just want to stop at these
Oh
problems.
yeah, Jenny, I forgot to tell you too, that kind of excited. Like I didn't even know about this, but my dad was talking to one of his best friends. He's a doctor at Mines.
Yeah.
And he was asking around if there was a summer program for me, and he reached out to my father that there is a research program and that he's an assistant professor at the bio building. So he reached out to him about me, and he seemed interested in me, and I told me to call him and email him, and I did, and yeah, I got accepted, and I start on the 15th. So
Yeah,
Woo!
congrats.
thanks.
Congratulations.
Pick them all up. Do everything you can, man. Pad your CV.
Yeah. So I hope it's not a problem, Jenny, because I actually might be busy with my intern because
You'll be busy like Trey and Luana are. Yeah. That's
yeah.
okay.
When does your class start? You said, bro, 15th?
15.
Yeah, 15th.
We'll be
So-
almost done by then. We'll have only 4 days left to class.
Yeah.
I think we. Oh no, like 19th or something.
I'll
like
keep
that.
you updated, Jenny, 'cause, he wants me to show up on the 15th at 9, but I think the next 2 days he says I can like choose my hours. So
Okay.
I'll
Yeah,
just let you know a week ahead of time. 'Cause I don't want to let you know like last minute.
And what we're doing this week, these 3 days, is to me, I think the hardest calculus concepts that we do. So
Okay,
this
that's good.
we'll do volume tomorrow, which is I think the hardest for most people. But what we'll be doing that last week is more kind of plug and chug using formulas, and we'll do some differential equations, but I don't think you'll struggle with that, honestly, either of you. So you
Okay.
could do it probably at your own pace or meet with me outside of class or in the evening if you have questions. Okay, you always can do that.
Okay.
All right, so let me rush this because I want to show you just one picture before Trey leaves. So there's that answer, and it's in foot-pounds. And then the last thing, once I assigned one problem that was like this, so I didn't want anyone to be confused. It has a picture like this, and it's like here, there, and it says find the work, and it just gives you the picture, right? So, and it has numbers and little blocks and squares and stuff, so it has numbers over here. I think this was 30 over here, this went up to 8, this was like 2 or something like that. Anyway, so it's just like that. So just remember, work is the integral of the force dx, which is also the area under the curve. Always just remember that. That's the whole point of the first half of Calc 2, that we're looking for the area under the curve. So if we could use our just old geometry formulas and find that area, we'd have it. So when you see one like that on the assignment, that's all you need to find your area. So we'd break it up into a triangle and a rectangle. So that would be 6. This one is, yep, length times width. This is the height, this is the width right here. And then this one is gonna be 1/2 BH. 1/2 the base. And the top height was 30. So in this example, you can barely see it. 1/2 times 2. So it's
30,
gonna,
right?
yeah, 30 plus 180. So this one would be 210. And then whatever label it has for the force, I forget on that one, if it has the if it's in metric or US customary, but let's just say if it was in metric, it would be joules. But they'll say in here, like right here, if this was meters, then you'd
Oh,
know that you're in joules. And if that was in feet, then you'd be in foot-pounds. So that's it for today. So no assignment 5 yet. Just get after your assignment 4. It's kind of long, so that's why I'm not going any longer for this class today. That's in web. Okay, guys.
So,
Thanks for being here. You're
Yeah.
awesome.
We'll see you in the morning, Jenny.
See you tomorrow.
Yeah.
Have a good day.
You too. Later, Angel.
see you, Trey.